Okay, so welcome to your introduction to quantum optics. This is lecture 13. We have only a few lectures left, like 4 lectures or something like that. And before we proceed, let me remind you where we were and what we have done so far. So let me go a bit to the beginning of the story. And I remind you that what we were doing in this part of the chapter, we were dealing with how to describe open systems. And in particular, we already did how to describe open systems with the example of an open cavity in the Heisenberg picture. And then last week, we did it as well in the Schrodinger picture. In the Schrodinger picture, which is where we are now, what we get is a master equation. And the idea of how to derive this master equation is we simply consider the evolution of the whole closed system, including the open system and the environment. And then we get a Hamiltonian for the system, a Hamiltonian for the environment, and some interaction between them. And something that is very important that will be clear today is that in this case, the interaction, we take that the coupling between the external modes and the internal modes, or the environmental modes and the system operators, is independent of the label or the frequency of the environment, okay? So when we do this approximation, and then we go to the interaction picture, so we end up with an equation for the reduced state of the system. So this is the trace over the environment, okay? So this is the full state traced, partial trace over the environment. We end up with an equation that is exact at least, assuming certain things about the environment, such as it is in a thermal state, or it's uncorrelated from the system state at time 0. We end up with an exact equation that for that state, that it's still a non-Markovian integral differential equation, and it's not easy to solve in general. However, we saw that we can do a couple of approximations, in particular, both of them related to neglecting effects that are of higher order in the interaction than 2, so order 3, 4, etc. And these two approximations, or the effects that come from higher orders, the first one is what we call the Bone approximation, in which we assume that the state, the total state of the system in the interaction picture, is the tensor product of, so it's an uncorrelated state of the cavity and the environment. And then we assume the absence of back action from the system to the environment, because environment is a huge thing that cannot be much affected by the interaction with a tiny system, okay? And then in particular, we just assume that then the external state is essentially the thermal state, the equilibrium state of the environment that we are working with. When we do these two approximations in the evolution equation of the state, again, as I told you, we are not saying that this is the state of the system, okay, of the full system plus environment. We are just saying that any effects that go beyond that cannot enter the dynamics of the system of the cavity up to order 2 in the interaction. And then when we do that, then you can, well, we did the calculation slowly, and we showed that you can find an equation for the state of the cavity already in the Schrodinger picture, in the original Schrodinger picture, that looks like this, okay? It has a Hamiltonian that is the original Hamiltonian of the cavity, and then some correction that comes from the environment, and in particular this injection Hamiltonian. I remind you, even though you have seen it already a few times, this injection Hamiltonian is the way in which we introduce, so here it is, any external lasers or any driving terms, any coherent parts of the environmental state. And in particular, it's always kind of a time-dependent force, okay? And this time-dependent force is just a Fourier transform of how are you exciting each frequency outside the cavity, okay, each environmental mode. So how is the amplitude of the coherent state for those modes? So that's the Hamiltonian part for the master equation, okay? But then we get other terms that all of them can be written in this form that we define as something called Lindblad form, okay? And we call this dissipative superoperator. And essentially, they bring in processes that are not quantum coherent in the sense that they can be written as a Hamiltonian, okay? This you cannot write as a commutator. And what we saw is that these objects here that we call the jump operators, so A and A dagger in this case, but in general, any jump operator J, actually has the interpretation of irreversible quantum jumps that the system goes through at a rate given by these rates here, okay? And whenever they happen, you go through an irreversible process that there is no way that you can come back from it, okay? At least not easily. You need to really be controlling, monitoring things from outside, see that the jump happened, and then undo the jump by knowing what was the state before or something like this. But it's not reversible. It's not easily reversible like the Hamiltonian part, that mathematically you just need to invert the sign of the Hamiltonian or the arrow of time, whatever, however you want to see it. So I told you that actually this form for the master equation, so in particular, this form for the master equation, is not something accidental, that this happens whenever you have the Bone approximation, so whenever you can do the Bone approximation, and you also have Markovian conditions. We will talk about Markovian conditions more today. And at the level that we know right now, Markovian condition simply means that the coupling with the environment is independent of the frequency, okay? But whenever you have these conditions, so Born and Markov, then you can always show that the system will evolve according to a master equation that has this Lindblad form, okay? So this is, then keep in mind that this form is something that we are going to use all the time. So some Hamiltonian and then some dissipative terms, we call them, even though they don't need to be always dissipation. Like for example, this one here, the jump operator is A dagger, right? So this means that in this process, this irreversible process, what you do is that you create jumps by creating a photon in the cavity, okay? But of course, because the rate of annihilation of photons, it's, you see it here in +1 gamma, so there is a balance between these two terms. And this is what makes you get to a thermal state, like we saw in the Heisenberg picture. You start creating and annihilating photons incoherently until they find a balance at specifically the number of photons n. And this we will see today explicitly through solving the same example as we did in the Heisenberg picture, but now in the Schrodinger picture. Okay, so then this is just the interpretation that I just told you about quantum jumps. And then this brings us to essentially today. So what is the plan for today? Today I will be solving in the first part of the class the example of an empty cavity driven by a monochromatic laser. We did it in the Heisenberg picture. Now we will see how to do it in the Schrodinger picture. And then we will move on to studying a different kind of open system. So another open system, which is an atom, okay? An atom in free space. You will see that that on itself is already an open system. And this will give us the opportunity to introduce several important concepts that we haven't done with the cavity, and in particular, talk more about the Markov approximation and about the full state of the system, including the environment and how the system and the environment get entangled and these kind of things. So I will show you all this today, or at least I will start and finish next week. Okay, so let's start with the example in the Schrodinger picture of the driven empty cavity. And as I told you already last week, so before we start with the example, it's important that I explain you a couple of general things about how to change pictures when you have a master equation instead of just a Hamiltonian. And also another thing that I will show you in a second. So we already went through this, but let me remind you that essentially what I told you is that imagine that you have a state in the Schrodinger picture, and now you want to move to a different picture, okay, some intermediate picture, and defined by a unitary transformation as usual. So the idea is that now, if I ask you what is the evolution equation for this state, of course, the Hamiltonian part, you just get the intermediate picture Hamiltonian that we know from the closed systems chapters, okay? But then we also have to transform the incoherent part or the special part of the master equation. And the special part of the master equation, it's easily transformed. It just gets the same kind of Lindblad form. However, now the jump operators are not the original jump operators, but just the jump operators transformed through the unitary transformation, okay? So it's very simple to change pictures in the master equation. It's just the Hamiltonian part as we did it already, and then the jump operators, you just change them through the transformation. Okay, then on top of this, it's interesting or it's useful to make the following definition. So useful definition, which is the following. So I am going to define something that, so for an operator A, any operator A, I will define something called the expectation value of the operator in the interaction picture, okay, at time t, which is the trace of the operator with the interaction picture state or intermediate picture state, okay? Note that this is not the expectation value of the operator, because I remind you, so again, this is not the expectation value of the operator, because the expectation value of the operator, it's a different object. It's, so if you want the expectation value of the operator, in the interaction picture, this would mean evaluating the interaction picture operator and then doing the trace with the interaction picture state. So this thing here is just the operator transformed by the unitary. Okay, this is how you write the expectation value. So what I am saying is that it will be useful to define another type of trace, okay, which is just the expectation value, but not the real expectation value, just using the state in the intermediate picture. And of course, by using this transformation, okay, we will see how you, once you know this object, you can always find this object here, okay? Because usually this transformation is trivial because it's a transformation that we know, we are inducing it, okay? But in any case, just keep in mind that we are going to use this object quite a lot today. So I will come back to that. So now the second kind of general thing that I want to explain to you, it's we are going to be talking all the time, or in quantum mechanics, we always want to know things about observables, and in particular about expectation values of operators, okay? And therefore, it's quite useful to derive an evolution equation, not for the state of the system, which is the master equation that we know, but for a generic expectation value of an operator. So imagine that I ask you, what is the expectation value of A? How does it evolve in time? So I want to find an evolution equation for the state. sorry, for the expectation value. So this is actually quite easy to write in a compact form in which the state doesn't play any role anymore. And you only need to evaluate commutators of the operator A with the Hamiltonian and with jump operators. And this is what I am going to show now. And it's not very difficult, but it has a couple of tricky spots, so I want to show you. So first of all, the expectation value of the operator A, this is nothing but the trace of the operator times the state, right? But now we have the time derivative, but the operator is independent of time in the Schrodinger picture, and therefore we only have the time derivative of the state. Now, we know the time derivative of the state because the time derivative of the state is just the master equation, okay? And I will just assume that we have a generic master equation. I should have it here. So just imagine that this is the evolution equation of the state, just a generic master equation in Lindblad form. So now I can substitute this, okay, in the time derivative. And what do I get? So I get just the trace of the operator A. And now the first part is the commutator, right? So we have the Hamiltonian IH bar, and then the commutator with the state. And now the second part, it's the dissipative terms, in which we can always write in the following form. So we will have again the trace of the operator A times the dissipators J, D. Okay, so up to here I didn't do much. I just substituted the master equation, but now it comes the funny bit. So if we want to compute the first term, okay? So the trace of A times the commutator with the Hamiltonian, we have something like this. So this, let me expand the commutator as H rho minus rho H. Okay, and now it comes the interesting part. I can, because of the cyclic property of the trace, I can always take this Hamiltonian and bring it to the left of A, okay? And then I am left with something like this. I am left with something that I can combine. So now once I do this, so once I bring H here, you see that rho appears in both terms on the right side. So this means that I can put together A times the Hamiltonian minus Hamiltonian times A. And what is this? This is just the commutator of A with H, okay? And we have the trace rho. So this is just the expectation value of the commutator of A with H divided by IH bar. Okay? So we have been able to find that the evolution of the state A has one term that is the expectation value of the Heisenberg equation. This is not a surprise. I mean, in the Heisenberg picture, if this would be a Hamiltonian problem, you would know that the time derivative of the operator is the Heisenberg equation, right? So if you just take the expectation value, then that's what you get. But we have been able to show it in the Schrodinger picture in this case. So now it comes the other parts. So for example, remember that this dissipator has, let me show you again. This dissipator has this kind of terms. So let me take this term, so J rho J dagger minus J dagger J rho. Okay, that's the first term I am going to take. So if I take this term, which means that I am evaluating the trace of the operator A, and now this operator is acting on J rho J dagger minus, and then J dagger J rho. Okay, this is the first part of the dissipative pieces. And now I can do, again, the same kind of trick. So here I have the state on the right. So now I want to write this term with the state on the right. And for that, I can use the cyclic property of the trace and simply moving this jump operator to the left of A, okay? So when you do this, it's very funny that what you end up with is, it's very easy to write, because now you see that you will have J dagger A, and then on the right, you will have J rho. But then in here, you already have J rho on the right, okay? And then A J dagger. So convince yourself that this will just be the expectation value of the commutator of J dagger with A times J, okay? And of course, now we can do the same with the last piece of the dissipator. So the other piece of the dissipator, the first part is the same, is A J rho J dagger. But now in the other part, instead of J dagger J rho, you have rho J dagger J. And this you can write as J dagger times the commutator of A with J, okay? And if you are wondering how, so I guess the easiest way is to, for example, in this case, so we can move A to this part and then A, J to this part, okay? And then you will see it right away. So just do it yourself at home to convince yourself that this is the case. But then this means that at the end of the day, so what I wanted to show you is that the time derivative of the expectation value of any operator can be written as the expectation value of the Heisenberg equation plus, and now the jump terms or the dissipative terms, they always contribute in the same way. So with the corresponding rate kappa j, you will get the expectation value of first, the commutator of the jump operator J dagger. So the jump operator dagger with A times the jump operator plus the jump operator dagger times the commutator of A with the jump operator, okay? So this is an equation that for anyone working with master equations, it's super useful, okay? Because as you see, nothing in here, so everything depends implicitly on the state, but in order to find the evolution equation, you only need to know the commutators between your problem operators, so the Hamiltonian and the jump operators, and the operator that you are interested about. And that's enough to write down the evolution equation of the expectation value of the operator, okay? So these are the two things that we need before we consider the example that we are going to study. So I remind you, first of all, how to move to a new intermediate picture, okay? Just transform the jump operators and the Hamiltonian as we know, and then how to find evolution equations for generic expectation value of any operator, okay? So with this knowledge, now we can consider the example, okay? So let's consider the example of an empty driven cavity. So empty means that we assume that the intracavity Hamiltonian is 0. Okay, so this is what we define as an empty cavity, and driven by a monochromatic laser means that this time-dependent force is just a periodic modulation. And this is what we call a monochromatic laser. Okay, so let me then write down the master equation. So just to remind you, so the master equation for the state of the cavity. So I will not write a cavity explicitly in the state. So this thing in here is the cavity state. I will not write the subindex cavity because we will be not working with anything that is not the cavity anymore. So I will just call it rho. And then we have the Hamiltonian terms. So in particular, we have this kind of Hamiltonian. So it's this, and then the driving term. Commutator with the state, and then the dissipative pieces. And the dissipative pieces, we have the jump operator A that annihilates photons from the cavity, and then the jump operator A dagger, which creates, if the temperature is not 0, creates excitations inside the cavity so that everything will balance out to a thermal state at the end. Okay, so a couple of things to mention here. So first of all, I remind you already. So I remind you that we already saw in the Heisenberg picture that the state of the cavity will remain Gaussian if it starts Gaussian, okay? And in particular for long terms, the asymptotic state will be a Gaussian state. And this is because the environment is Gaussian, and the full Hamiltonian, the full interaction Hamiltonian, and the Hamiltonian of the system and the Hamiltonian of the environment are all quadratic Hamiltonians. And we already saw in the second chapter that quadratic Hamiltonians keep the Gaussianity of the state. So that's one thing we know, but now we also see in here that another way of see the Gaussianity when you deal with a master equation is in the following way. So this master equation, you see that it's quadratic in annihilation and creation operators, right? So the Hamiltonian is, it has a linear part and a quadratic part. And the dissipator, because the jump operator is linear in the annihilation and creation operators, okay? Then the dissipators will be quadratic. So whenever you have a master equation that is quadratic in annihilation and creation operators, or position and momentum, then the state will remain Gaussian if it stays Gaussian, and the asymptotic state will be Gaussian, okay? That's something that you can prove, and it just generalizes what we saw with Hamiltonians. So we already saw it with the Hamiltonian, right? That quadratic Hamiltonians keep the Gaussianity, so quadratic master equations keep the Gaussianity as well. Okay, so knowing this, now we understand that we only need to evaluate first and second order moments, okay? On the other hand, you see that this is a time-dependent master equation because we have these driving terms, this monochromatic laser term that depends on time, right? So because this depends on time, it makes the problem more complicated. So it's useful to always move to a picture where the master equation becomes time independent. And for this, in this case, as you are already familiar with, the easiest thing is to move to a rotating picture. And a rotating picture is just a picture defined by the unitary transformation that discounts the free evolution of the bosons, of the bosonic modes, at the frequency that you want the system to be rotating at, which is the laser frequency. So in particular, with this transformation, then the transformation of the annihilation operator A, it's nothing but literally a rotation in phase space. So it's this linearly time-dependent phase. Okay. And therefore, this brings us to the following master equation. So first of all, we get, so now we are in the intermediate picture. So we have to transform the Hamiltonian, right? Transform the Hamiltonian means that we have to take the Hamiltonian in here and we have to apply this transformation. But when we apply this transformation, as you see, the transformation applied on a dagger will bring the exponential of plus I omega LT that will cancel this. Okay, it will cancel this exponential. The same with this exponential, it's canceled. And now this term is invariant because a dagger A, because this is a phase, remains invariant under the transformation. And now we also have, I remind you quickly, to remove this term in here. So u dagger time derivative of u, which for these simple cases in which the u is just the exponential of a Hamiltonian, is just the Hamiltonian, okay? So we have to remove the omega L. So at the end of the day, we will have the same Hamiltonian that we had by removing the time dependence. And here, instead of omega c, we will have the difference between omega c and omega L. So essentially, we have a master equation that looks like this. I delta a dagger A plus epsilon A dagger minus epsilon star A. Oops. And this is commutating with the state in the intermediate picture, in the rotating picture. So, and I remind you that this delta is just the difference between the laser frequency and the cavity frequency. And now we need to transform also the dissipative terms, okay? So in particular, we need to transform, first of all, this dissipator. So the one with jump operator A. But look at what happens. So the jump operator A, in the new picture, we have to transform it. So we have to apply this transformation and we get this phase. But I remind you that in the expression of the dissipator, we always have the jump operator and the jump operator dagger, okay? So we always have J and J dagger. So we will always have A and A dagger. So the phases will cancel. So again, this transformation leaves invariant the dissipative pieces, okay? So in the new picture, you still have as jump operator the same, A, acting on the intermediate picture state, and the same jump operator A dagger acting on the intermediate picture state. Okay? So is this clear? So the nice thing now is that you see that we end up with a master equation that it's just similar to the original one, but now we don't have any time dependence. Okay? So now everything is time independent, and now we know that the steady state that we will find, that the asymptotic state that we will find for long times, will be independent of time, okay? And this is why we do these things. So then, finally, now that we have the master equation, now I can ask you how to evaluate the evolution equation for any expectation value of any operator. So of course, we will care about first and second order moments. So we will care about when this operator capital A is A or A squared or A dagger A. But for a general one, if I ask you, what is the time derivative of the expectation value of A in the intermediate picture, because it's the state that we have in the master equation, Then, using the thing that I just showed you in the previous blackboard, you will just have to evaluate this. So first, the Heisenberg equation. So we have the commutator with the free term A dagger A. Then we have the commutators with the driving terms. So we will have A with A dagger. This is a minus. And then minus star. And then A with A. Okay. All of this is in the interaction picture. And then we have the terms that come from the dissipators. And these terms, as I said, they can be written as the commutator of the jump operator dagger. So in the first case, the jump operator is A, so we have to put A dagger, times the jump operator, plus now the jump operator dagger, times the commutator of A with the jump operator. So this is the first term, and then the second dissipative term, it has A dagger as jump operator, so it will be kind of the opposite. So it's the commutator of A with capital A times A dagger plus the commutator, plus A times the commutator of A with A dagger. Okay? It's so difficult. Okay, I think you can see it. So now, if I want the expectation value of any operator, I just have to plug it in this expression, and knowing the commutators, the canonical commutation relations, I can evaluate the corresponding equation. So in particular, so if we apply this to the first and second order moments, so in particular, so if I ask you what is the evolution of the expectation value, by the way, all these expectation values are with respect to the intermediate state, or the state in the intermediate picture, okay? So then all you need to do is come back to the equation that we had, plug the annihilation operator instead of the operator A, and then let me just go through it once with you. So if we put in here the annihilation operator, then we have the commutator of A with A dagger A, and that will give us an A, okay? Then A with A dagger will give us 1. A with A will give us 0. A dagger with A will give us -1, and then we have an A. Then A with A 0, and the same here. A with A 0, and A with A dagger, it will give us +1. So in total, when you put everything together, just check yourself that you will get the following equation. Very simple equation that we actually already found out, or something similar in the Heisenberg picture, okay? So you see that it's a very simple linear equation for the expectation value of A. Now, if you do the same with the expectation value of A squared, then you will get something relatively similar. So you will get first something that depends on the linear term, and then you will get an expression that depends on the second order moment. Okay? And now if you do the same with A dagger A, this is the last one we need, then you will find this expression in this case. So this, and then minus 2 gamma, and in here we have A dagger A, plus this should be minus gamma, sorry, N. Okay? So as I said, just convince yourself of this. So you just need to take the operator A square, put it in this equation and evaluate the commutators, and the same with the operator A dagger A, okay? If you do it, you will get these 3 equations. Now, I also remind you that for the second order moments, we usually care not about A square, but about the fluctuations square. So in particular, what we care about is what is the evolution equation for the fluctuations of the operator squared. And this is very simple to find, and it gives you an equation that is very easy. That's why I want to write it down. So I remind you very quickly that delta A is nothing but A minus the expectation value of A, okay? And of course, I will always define it in the picture where we are. So then if you take this and you expand, what you get is something very simple. It's just the time derivative, or the expectation value of delta A squared is just A squared minus the expectation value of A squared. Then you can take the time derivative and you find the time derivative of A squared minus 2 times A and time derivative of A. And you know the time derivative of A squared, you have it here. You know the time derivative of A, you have it here. When you compute this expression, then it collapses to something much more simple, which is just this part in here. Okay, so we get exactly this part that we had in the evolution of the square. Okay, the evolution of the second order moment. So you can do the same for the time evolution of delta A dagger delta A instead of just A dagger A. And with no surprise, you get exactly this part in here, okay? You get exactly, so minus 2 gamma that multiplies A dagger A, sorry, delta A dagger delta A minus N. Okay? So then now you see that we have 3 very simple equations to solve. So we have the evolution equation for the first order moment and the evolution equation for the second order fluctuations, okay? Second order moments or for the fluctuations. Then it's completely trivial for you to see that the asymptotic solutions, which is what we care about, the asymptotic solutions are the following. So the limit, so when gamma t goes to infinity of the first order moment, this will be equal to what? It's actually completely trivial to see from the equation. Because as I said, this is a linear equation and it has dissipation. So in the long time limit, you will find some static expectation values and some asymptotic stationary expectation value. So all you have to do is put the derivative to 0. And then you see that delta A, so sorry, the expectation value of A becomes epsilon divided gamma minus I delta. So let me write it down. So epsilon divided gamma minus I delta. Now we can do the same for the second order moments. Limit when gamma t goes to infinity of delta A squared this is equal to 0. And again, you can see it because the equation is directly proportional to the expectation value. So when you set to 0 the time derivative, you get just that the expectation value is equal to 0. And then finally, we get the asymptotic value for the expectation value of A dagger A. And all this is in the intermediate picture. And this is precisely the definition of the thermal photon number, okay? And you see it again from this expression, because in order for this derivative to be 0, this has to be equal to this, okay? So in other words, coming back to the state, so now we know everything about the state. We know the first and second order moments. So we can say that the state in the limit of t going to infinity, of long enough time, is Gaussian. And it has the following Gaussian objects. So first of all, the displacement of this state is just 2 times the real part of the expectation value of A. So gamma minus I delta, and the imaginary part of the expectation value of A. So that's the mean vector. And then the covariance matrix. If you remember, we already saw how to find the covariance matrix just from the definition of this and this. So you can come back to check it, and it's very easy. This is just 2n plus 1 times the identity. So what is this? These two things together tell you that you have a displaced thermal state, which is something that we already knew from the Heisenberg picture, okay? So now in the Schrodinger picture, with evolution equations for expectation values, we have been able to find what is the state of the system in the intermediate picture, okay? So before we make a break, let me take maybe another 10 minutes, and then I finish this part of the chapter. So we have taken, so we know now the state in the intermediate picture. So we know rho intermediate, but we want to come back to the Schrodinger picture. So we can do this in a couple of ways. So let me just show you both ways. So coming back to the Schrodinger picture. So, well, I don't need to put stars. So first of all, we want the real expectation value of A, okay? The real expectation value of A, as I told you already, so let me just remind you, this can be written as the intermediate picture operator times the intermediate picture state, the trace of that. And at the same time, the intermediate picture operator, that's just UC dagger, A UC. But we also know how this operator transforms, just with the phase, with this simple phase. So in particular, we get the rotating phase, but then we get the same operator A. So at the end, this is the relation between the real expectation value. So the expectation value as you would measure it in the laboratory, okay? And the expectation value, the mathematical one that we defined in the Schrodinger picture. Sorry, in the intermediate picture, okay? So they are related just by the rotation induced by this phase. So of course, This means that when time goes to infinity, so when gamma t goes towards infinity, then this becomes just the expectation value that we found in the interaction in the intermediate picture times the rotation. Okay, that's a real expectation value of the state in the Schrodinger picture. Now the same you can do for delta A square, and you will find e to the minus 2I omega LT and the same expectation value, but in the intermediate picture, okay? Which essentially means that when gamma t goes to infinity, this goes to 0 as well. And finally, you can do the same for the expectation value of delta A dagger delta A. And in this case, because it's just a phase transformation moving from one picture to the other, it just doesn't change at all, okay? So you get that this is the same, both in the real or original Schrodinger picture and in the intermediate picture definitions. And in particular, this was M, okay? So now that you know the real expectation values, okay? So the expectation values in the Schrodinger picture, then you can write down that the state, the real state, so the Schrodinger picture state is Gaussian with a mean vector d of t that is just, it just have the real and the imaginary parts of this, okay? So because of that, it can be written in this very simple form. So cosine of omega LT, sine of omega LT minus sine of omega LT cosine of omega LT times the mean vector in the intermediate picture, okay? And this matrix in here is just a rotation. It's a rotation matrix with angle omega t, so it's rotating in time. And the covariance matrix is just exactly the same. It doesn't change, okay? And you see it doesn't change because you get the same second order moments in the Schrodinger picture and in the intermediate picture. So there is another derivation I like a bit more because it's more elegant, that is based on Gaussian physics, which is the following. This state, so let me show you, this is an alternative derivation. So instead of having to come back to find the expectation values of the operators, okay, from the expectation values of the operators in the intermediate picture, you can always do the following. You know that the state in the Schrodinger picture is just the state in the intermediate picture, but applying the transformation, well, applying the transformation back to the Schrodinger picture, okay? But now you know that this U is a Gaussian unitary. Okay, and in particular, it's a Gaussian unitary that you know how it acts on the positional momenta. It just acts with this. It's a phase transformation, so it acts with this rotation. This is something we saw in chapter 2. Okay, and we already saw in chapter 2 the transformation rules. When you apply a Gaussian unitary, how do you change the first and second order moments, the mean vector and the covariance matrix of the Gaussian state, right? So if you remember, this implies that the D, so the display, the mean vector of the transformed state by the Gaussian unitary is just applying this transformation, this linear transformation in the phase space. And the same for the covariance matrix. Now we have to apply the transformation. So this and then transpose. Okay, but because this is just proportional to the identity, so the covariance matrix is just proportional to the identity as we have seen, then this is nothing but, again, the same matrix. So it's invariant under the rotation. Okay? So essentially, this is kind of a more elegant way of solving the problem. And then, just to finish, let me discuss how this state looks in phase space. We already saw it in the Heisenberg picture, so let me just fetch it from there. But also, I failed to mention something when we did the Heisenberg picture example, so I will use it now. So let me take this figure. And let me come back. So this is something that we already saw in the Heisenberg picture. So in the rotating picture, okay, this is in the rotating picture. We have a state that has an uncertainty. So it's centered at this value given by how strong you are driving, okay, and how far from resonance you are and so on. We already discussed very much about this. And then the fluctuations around it are circularly symmetric because you have a thermal state and the amplitude is not 1, but 2n plus 1, as corresponds to a thermal state, okay? Now, what I failed to mention in the Heisenberg picture is that, of course, this is a static state that it's only true in the rotating picture. So when you are in the rotating picture, this is what you see. But in the laboratory, you are not in the rotating picture. You have to come back to the stationary frame and then see how the state rotates. And then the state, apart from this, it has this rotation in the mean, r omega t. So this means that this state in reality is doing something like this. So it's moving along a circular trajectory, okay, at angular speed omega L. Okay, so pretty simple. So if you drive a cavity and you have a thermal environment and you are driving the cavity with a monochromatic laser, you just get that the state inside the cavity will be a displaced state. So it will be a thermal state that is displaced in the, Jinan mentioned, I always make this mistake. I don't know why I want things to go anti-clockwise. Okay, so this is clockwise, okay. So anyways, in any case, it's rotating in the, is rotating in phase space. So the mean is rotating in a circle, okay? And then it has these thermal fluctuations around. So you see that either in the Heisenberg picture or in the Schrodinger picture, now you know how to solve open problems, okay? So I think that we are now in a good moment to do the break, because now we will move on to understanding some more things about open systems with another example, which is the atom in free space. So let's take a 10 minutes break. Maybe we can start again in, I don't know, 2:10. Yeah. So see you at 2:10. Okay, so now that we have this Schrodinger picture approach, let me go a bit deeper on it, and I will do it with one specific example that I call incoherent atomic processes. But in reality, we are only going to study one incoherent atomic processes, and then in the homework, you will study another one. So there are two very important incoherent atomic processes. One is called spontaneous emission. This is the one that we are going to focus on in here. And then another one is called dephasing. Maybe you have heard about it, about dephasing. And that's usually one that destroys quantum coherence. And then maybe you have heard about it in the context of losing coherence in kind of quantum computers and so on, or this thing that people call decoherence, okay? So what I am going to tell you now, in the notes you can find it in the first and second parts of section B, and it's the following scenario. You will understand why I combine both of them. So consider this scenario here. So we are going to consider now that we have a free space. Okay, so this is the Z direction. We have free space. So again, I remind you that we are within this 1D approximation or quasi 1D approximation. So for us, free space is just one-dimensional. And then in here, we put at some location, we put a two-level atom that will have an excited state and a ground state. Okay, so we have a two-level atom that it's at some location, Z0. Oops. It's a location Z0 that we will later take equal 0, but it's not relevant. And then now we ask ourselves, okay, we have an atom in free space. We excite it, okay, or we create any state of the atom, but not the ground state, any other state. What happens with the excitation that is contained in the atom? So in principle, the atom is interacting with the electromagnetic modes that are all around the atom, okay? We are in free space, we have all the possible modes, and in particular, in free space, we will have waves, or if you take the plane wave basis, you will have modes that are propagating to the right, and therefore have wave vector that is positive, and then you will have modes that are propagating, to the right, and then to the left that have wave vector that are negative, let's say -k and +k, okay? So then, and of course we are in free space, so we have all the available case, all the possible wave vectors. So this is, again, a scenario in which we actually have a small quantum system, which is our atom, that is a two-dimensional Hilbert space, interacting with a huge system, which is all the modes of free space. So in this situation, we are going to study how to find, or in which phenomena we are going to find for the reduced dynamics of the atom, okay? So first of all, let me remind you that in the case of the atom, so within this two-level approximation, the atomic Hamiltonian, it's nothing but, so let me write it as, so it's the Hamiltonian of matter. So this is the matter that we are considering. And we call epsilon to the, or h bar epsilon to the energy difference between the ground and the excited state, the transition energy. And then we have the Pauli matrix, the Pauli operator set. And so this is one thing. Then the other thing that we need to do is we need to develop a quantum theory for the electromagnetic field in free space, okay? So this is the first section that is called field quantization in free space. So in principle, we have not done this yet, because what we have done is quantizing the electromagnetic field inside an optical cavity. okay? And of course you could tell me, but just take the mirrors of the cavity to infinity, okay? And then that's free space. But we have used boundary conditions of the mirrors. And in particular, you remember that in the cavity, we have the modes propagating to the right and the modes propagating to the left. They are indistinguishable. So that's a single mode that creates a standing wave. That's our description. So in free space, you don't have this property, like the modes propagating to the right and the modes propagating to the left are independent, are completely independent. And therefore, you have to do a quantum theory that takes into account that these modes are independent. So you can find this. So this gives us an excuse actually to do a quantization in a little bit of a different way. Instead of based on quantizing position and momentum, we do it based on quantizing the normal variables of harmonic oscillators. The normal variables were this complex variable, okay, that contains x plus IP. But you can find this in the notes. It's really simple. It's very similar to what we have done already for the cavity. So I recommend you to check it out. But in here, I will just give you the result because I think we don't need to go through it again. And therefore, let me just tell you how is the quantized electromagnetic field. Electromagnetic field in free space. So the quantized electromagnetic field in free space, it's essentially what you already know from the cavity. So we will have some polarization along the x direction we take it, for example. Then we will have a sum over all the available wave vectors, but in this case, that means all the wave vectors in free space. So from minus infinity to infinity. Then we will have this normalization factor that we choose such that the energy matches the one of a collection of harmonic oscillators. And in the case of free space, it looks like this. It's actually the same that we already found inside the cavity, but parameterized by the wave vector instead of the frequency. And now it comes the important part. Now we will have so we can define annihilation operators for waves of wave vector k, for modes of wave vector k. And this will be multiplied by the corresponding wave, okay, propagating in the k direction. And then, of course, we have the Emission conjugate, which is the annihilation operator. Okay, so this is the expression. I don't think I surprised you very much. This is the expression that you get for the quantized electromagnetic field in free space, where modes with k and minus k are independent. So in particular, this independency of the modes, you see it explicitly in the commutation relations, because the commutation relations that you get in this quantum field theory are continuous commutation relations, so continuous canonical commutation relations, but now in terms of wave vectors instead of frequencies, which is what we did for the optical cavity. So in particular, we get these commutators here. Okay. So note that this is quite interesting because if you think about what we had for the open cavity, compared to this situation in here, it's like we have twice the number of environments that the cavity had. Because in the cavity, we only had like modes that were described on the, let's say, on the right of the cavity, right? And here we will have those modes and also modes that propagate in the opposite direction. So in one way, what we are going to find all the time is a factor 2 with respect to things in the cavity, okay? So we will find dissipation, we will find all these things, so master equation and so on, but just with an extra factor 2 because we have like 2 environments. So, but this will come very naturally. I just want to mention it now. So on the other hand, so this is the electromagnetic field, and how about the Hamiltonian? So the Hamiltonian of the electromagnetic field in free space, as you can imagine, so let's call it HL. This is just for each mode, for each oscillator labeled by the wave vector K, we just write down H bar omega, so H bar C wave vector K. So that's the frequency of the oscillator, and then A dagger K, AK. So this is the Hamiltonian for the electromagnetic field in free space, okay? So I have condensed everything about quantization in free space in this small space. So, but I recommend you again to go to the lecture notes and just check how to quantize properly and so on. And let me know if you have any questions about it. So let me see if I want to say something more here. Not for now. So let me move on. Let me move on then to how we describe the interaction between the atom and the external electromagnetic field. So this is something that we know very well from the chapter about light-matter interaction. And in particular, if you remember, the light-matter interaction Hamiltonian, we could write in this way. So just, at least when the interaction is weak, we take the electric field at the position of the atom, and then we multiply it by the dipole moment of the atom, which is just E times the position, not the position, the relative coordinate between the electron in the atom and the nucleus of the atom, okay? I have the feeling that there is a minus sign that doesn't match. So let me go quickly to that chapter and we see it, because I think I put a minus extra that should not be there. So let me see, where do we have the light matter Hamiltonian? Yes, yeah, exactly. So the dipole moment is minus that relative coordinate, if you remember. And the light matter Hamiltonian has an extra minus as well, right? It's minus E times the dipole moment. So then in total you have a plus. Okay, good that I found out before anyone complained. Let me check. Yeah, so then we have a plus sign in here altogether. Okay, so this means that essentially, if now we expand using the two-level approximation for the atom, and we also use the rotating wave approximation for the interaction, okay, then I don't think I surprise you if I tell you that we get a Hamiltonian that looks like this. So we have the sum over all the possible wave vectors. We have a coupling J of K, and then we either create a photon by making the atom decay from the excited to the ground state, or we absorb a photon and excite the atom. Okay? And in particular, this is not super important. Well, it will be a little bit important, not the specific expression, but at least how it depends on the wave vector. This coupling, okay? This coupling, it's exactly equal to the following. So yeah, I'm just checking. So this is essentially the dependence of the coupling on the wave vector k. Then we have the matrix element between the ground and the excited state. So the dipole moment element, matrix element of the relative coordinate in the x direction, because the field is polarized along the x direction. Otherwise, it's whatever combination you get. And then we get also the shape of the mode k, which is just this plane wave at the position z0. And just for simplicity, we are going to take z0 equals 0. Of course, for a single atom, nothing can depend on your choice of z0, because no matter where you put the atom in the z direction, it sees a continuum of modes of the electromagnetic field, so everything should be the same. However, this phase factor here can play a very, very fundamental role if you have not a single atom, but two atoms separated by some distance, okay? Then, depending on whether the distance between them matches the wave vectors that are available for their transitions and so on, then you can get really interesting effects such as superradiance and subradiance. And this is something that people do a lot of research on, especially now that we have a lot of experimental platforms where we can implement this kind of Hamiltonians. But this is a story for advanced research thing. But I just want to at least let you know that this exists. And in our case, we will just take z0 equals 0, and we will further assume that this thing in here is real, okay? Just for simplicity. So that we have done already, actually, when I wrote this expression, okay? That G is real, it's already implicit because otherwise it will be G here and G conjugate in here, okay? So perhaps I should be a bit careful and I should write exactly that, because I still didn't do the approximation in there. So sorry for disrupting your notes, but maybe it's better if I write it properly, so later you don't have any doubts, okay? So this is what you will get. And of course, when G is real, you can just pull it out. Okay, then I have to make one remark before I continue. And the remark is as follows. So there is something weird about this coupling, okay, which is that if you think about what happens to this coupling at very short distances, sorry, very short wave vectors or very large wave vectors, in particular is more dramatic if you think about large wave vectors. So when k goes to infinity, okay, when k goes to infinity, this is unphysical. So this is unphysical because it goes to infinity. Okay. So this means that this model that we are using, it cannot be right for high energies, okay? When k is very large or the frequencies are very large. And this is obvious because if you think about it, when the k is very large, it means that the wave vector, sorry, the wavelength becomes very small. And at some point, the wavelength is so small that our model, in which we are assuming that the electromagnetic field doesn't vary, so it's the same along the whole space of the atom, that's no longer true anymore, okay? And moreover, if the frequency is too large, all this dipole moment approximation that we are doing and so on breaks down, because you can start creating electron-positron pairs and so on, and everything goes to hell, okay? So you need to use quantum electrodynamics properly and so on. So in other words, this coupling that we are taking, it's not the real situation for high energies. And you can also show that it's not the real situation for low energies, okay? For very large spatial scales. However, in our case, this is all irrelevant because, so this is unphysical, but it's not a big issue because let's say that in our case, only wave vectors k around the frequency of the atom, so epsilon divided by c, will contribute. Okay? This is something that we know from the previous chapters, right? That if we have this weak interaction, that then only the processes which are more or less resonant with the transition of the two-level system will contribute effectively to the dynamics. So then all the large K and small k will effectively not have any effect on the system, and therefore we don't care really about how is the coupling with those modes. Okay, so this is similar to what we saw with the cavity. So this is the first thing. And then now that we have a model for the interaction between our open system, which is the small atom, and the environment, which is the free electromagnetic field, now we can do what we did for the cavity. We can trace out the environment under certain approximations and so on. So, and in particular, so let me show you what happens under the same approximations as in the cavity. So under the same approximations as with the open cavity, and let me remind you what are these approximations. So the first approximation is that GK, we say, oh, it's independent of the frequency, okay? So we have seen that it depends on the frequency, but we assume that, okay, around the frequencies we are working with, we will always more or less have something similar, and we call it just square root of gamma divided by pi. But in this case, if we want the master equation to look pretty, then we have to put a C and a 2, okay? The 2, this factor 2 comes precisely from what I told you, that we have twice the number of environments, okay? You see the first 2 popping up. And the C comes from the fact that we are labeling the external modes with the wave vector, not with the frequency, okay? So this G has not a square root of frequency units. It has a square root of wave vector units. Is that true? Yeah. So, okay. Then the second approximation that we did is we assume that when the interaction is very small, we can extend the frequency integrals from instead of 0 to infinity, from minus infinity to infinity. So let me show you how this appears in here. So in this case, we will have always integrals in wave vectors. So things of this type. So we will be integrating some function of the wave vector k between minus infinity and plus infinity. However, let me just take functions that depend only on the absolute value of the wave vector. This is what happens naturally in our system, as you will see. Then I can do a couple of manipulations here. First of all, so because the function is symmetric in k, I can just do 2 times the integration from 0 to infinity. Okay? So you see now the factor 2 appearing again, okay? And now, typically, in order to avoid confusion, okay, because this k is only the positive case, in order to avoid confusion, we usually define the frequency actually. So we usually change from the wave vector to the frequency. And then we get an integration that looks more like the one that we had for the cavity. So we get d omega and then f of omega over c divided by c. Okay? And now we can do the approximation that only omega frequencies contained in the interval epsilon minus gamma and epsilon plus gamma will contribute. So this is something that we expect and we kind of know from the previous chapters. So we can mathematically, for convenience, extend the integration to minus infinity in frequencies. Okay? So if we do these two approximations, and I remark one important thing, this integration here from minus infinity to infinity, this has nothing to do with this integration here from minus infinity to infinity. These negative k modes are physical. They are waves propagating in the negative k direction, so in the negative z direction, okay? These negative frequencies are really artificial modes that we have put in there just for mathematical convenience. This is very important because I have seen people make the mistake that, oh, we already have the minus infinity here, so we don't need to extend it here. Okay, that's not true, okay? So this is the correct pathway. And so these two approximations alone, remember that these two approximations already imply the Markov approximation together with the Born and absence of back action approximations. And then the other thing that we assume, and we are going to assume here as well, is that the environment is thermal, okay? So it's an environment at thermal equilibrium, except for some lasers that we can have. So remember that this means that we have some displacement added to the external state and so on. So if you do these approximations, which are exactly the approximations that we did for the cavity, but now for the atom, we get a very easy master equation, which is very similar to the one that you found in the cavity. So in particular, this will be the master equation that we get for the atom. So let me write it down. So we have the Hamiltonian of the atom, then we have an injection Hamiltonian, just like we had for the cavity. This will come from the lasers. And then we have dissipative pieces. And what are these dissipative pieces? So again, Lindblad form. And now instead of the annihilation operator, we have the lowering operator of the atom, so the sigma operator, so the operator that brings you from the excited to the ground state. And at a rate that will balance out for a thermal state in the asymptotic state, in the asymptotic limit, we get the same kind of Lindblad term, but with jump operator, racing operator. So now we create transitions from the ground to the excited state, okay? So this is the master equation. This is the master equation of the open atom under these approximations that we made for the cavity. And let me just tell you that the injection Hamiltonian, it takes the same form as it was in the cavity. So it's some time-dependent, let's say, force that now excites coherently the atom. So this is essentially the semi-classical Rabi Hamiltonian that we studied in the third chapter. Okay, so this is what we get, and we have come a long way, because from the third chapter, in which we only had the Rabi Hamiltonian, now we know that in a real experiment we will also, whenever we are driving the atom, we will always have as well some dissipation or interaction with the environment. And you have to be very careful to design your experiment such that this either doesn't matter if you are really using the Rabi Hamiltonian for doing some coherent processes, or that you take it into consideration when you model your experiment, okay? But anyways, now you see that this is essentially what we get for the master equation of the open atom under these approximations. So in this case, it's a little bit different, because in the cavity, I remind you that the coupling was proportional to the transmissivity of the mirror. And the transmissivity of the mirror is something that we control. So it's something that we design. So we design a mirror that has a transmissivity that doesn't depend on the frequency. Of course, in the atom, this is not true. In the atom, this coupling is something fundamental, okay? It's something that comes from first principles. And in particular, we have seen that for optical frequencies, it's okay to approximate it for a square root of k dependence, so a square root of the frequency, okay? This means that this approximation that it's almost constant, almost flat, maybe is not a good one. So then we have to see what happens when we cannot do that approximation, okay? So this is what we will do later. But the first thing I want to do is I just want to take this master equation, but keeping this in mind, and we will see how this gets corrected. But we will take this master equation, and we will see the effects that this master equation has on the atomic states, okay? So for this, so what time is it? 2:45. Yeah, let's make a break now, and then we finish all the rest of the things until we can, and we can meet up at 2:55, okay? And then we do 45 minutes more. Okay, so as I said, what we are going to do now is we are going to use this master equation to understand what is the evolution of the state of the atom and what is the asymptotic state of the atom. Yeah. So I'm sure that you already have some bets about what is the asymptotic state of the atom. Not many things can happen depending on the situation that we have. And in particular, we are going to study one specific simple scenario. So consider the following one. So we are going to not drive the atom, so we will not have any lasers, okay? And even to make it simpler, because all the physics I want to discuss occur already in this situation, we will put the environment at 0 temperature, okay? So this means that the environment is in the vacuum state. Okay, then let's see what happens. So for this, the first thing I need you to remember is that the state of an atom, okay, the atomic state can always be expanded, if you remember, in terms of the identity and then the Pauli operators with some coefficients that we call the Bloch coefficients or the Bloch vector. And in the complex form, we had something like this. Okay, so just to remember that the description of a two-level system can be done in terms of something that we call the Bloch vectors, which are the coefficients in front of sigma set, and the x and y components of the Pauli operators, or the raising and lowering operators. And moreover, I remind you as well that it was very easy to find this B and B set because they are just expectation values of the corresponding Pauli operators. Okay? So then if I ask you now how a state evolves, what I am asking is find me the Bloch equations, find me the evolution equations for these coefficients. But these coefficients are expectation values. And we have just seen, okay, in the first part of the lecture, how to find evolution equations for expectation values from the master equation. So then just let's do that. So if I ask you what is the time derivative of B set, for example, or let me start with B, then this is the time derivative of the expectation value of sigma. But now we go to the master equation, and in particular, let me remind you once again this expression here. So for any master equation in Lindblad form, the time derivative of expectation value is equal to the corresponding Heisenberg equation, the expectation value of the Heisenberg equation, and then these funny commutators with the jump operators. So this is all we need to do in order to determine the expectation value of sigma and sigma dagger, but now with this master equation. But this master equation, even more trivial because there is no injection and n is equal to 0. So there is only dissipation, proper dissipation, only emission of photons from the atom, but not absorption, okay? So in this case, we have only one jump operator, which is the lowering operator. And you can see that the Heisenberg equation of motion is just this one in here. So you have the commutator between sigma and sigma set. That's the Hamiltonian. And then the part corresponding to the jump operator, it's only the one with the jump operator sigma. And in particular, only the term that it's jump operator dagger operator and then jump operator, okay? Now, this commutation relation, if you remember, or you can just check it out again, this is just 2 sigma. Now, this commutator in here, it's a sigma set. And when you multiply sigma set times, so sigma set times sigma, what you get, so all this multiplication, it's equal to minus sigma. Okay? So when you put everything together, you just get in here the expectation value of sigma, and you just get in here the expectation value of sigma. Huh. So easy, because now we have in here that this is equal to minus gamma plus I epsilon B. Okay? Now, what happens with B set? So B set is the time derivative of the expectation value of sigma set. So, and if you do the same game, you will find that this is just equal to minus 2 gamma and then B set plus 1. Okay? So these are the evolution equations for the Bloch vector components. And this automatically means that the B of t is just equal to the B of 0 and then an exponential of minus gamma plus I epsilon t. And then B of c, it's equal to BC of 0 plus 1 exponential of minus 2 gamma t minus 1. Okay? So you can solve these equations very trivially. These are just linear equations. We have done it already a few times. And this is the solution that you get. So what is the difference with the purely Hamiltonian situation? Remember that in the purely Hamiltonian, what we got was that B set was constant, B set 0, and we also found that we had precession around the set axis, which was given precisely by this exponential of minus I epsilon t. So now, on top of this precession around the set axis, what we have is decay. So we are precessing around the set axis, but also spiraling towards the axis. And in particular, we are spiraling towards B going to 0 for gamma t going to infinity, and B set going to -1 for gamma t going to infinity. So we are going precessing around the set axis, we are falling into the south pole, okay? So in other words, the limit when gamma t goes to infinity of rho, so the atomic state of t, is just the ground state, okay? And importantly, for any initial state. So this situation that, I mean, at the beginning when this was discovered was really, really shocking, because this is just telling you that if you put an atom in free space and you excite it, okay, you put it in the excited state, if you just wait, you just don't do anything, you just wait, it will spontaneously fall to the ground state and emit a photon, okay? Without absolutely doing anything. This is just because vacuum, because empty space is actually not empty, okay? It has quantum fluctuations, and the vacuum fluctuations are enough to trigger this, this process of, we call it spontaneous emission. Okay, so this is one of the most important kind of processes in quantum optics. And in particular in atomic physics, it's present in every experiment, so you have to be extremely careful to describe it properly. So, but now there is a specific interesting case. So let me consider one interesting case, in particular, an interesting initial state. So imagine that I put as initial state the excited state, okay? So we start from an atom that is excited. So this means that B of 0 is equal to 0, and that this set of 0, it's equal to +1. So we are in the north pole of the Bloch sphere, okay? Then, according to what we have just seen, so the solution that we have just seen, this atomic state at any time t will be equal to -2 gamma t, the excited state, plus 1 minus E minus 2 gamma t, ground state. Okay? So this is very interesting because this is telling you that E goes to, so the excited state goes to the ground state, but going through all possible mixed states. Okay, mixed states of excited and ground. So in particular, there is a time, so in this time, so when the time is equal to the logarithm of 2 divided by 2 gamma, okay, then actually the state has a balance between excited and ground. So the probability is 1/2 of being in any of them. So this mixed state, it's the maximally mixed state, is what we call the maximally mixed state in dimension 2. Okay? So And one further consequence of this is that except for time equals 0 and time equal to infinity or going to infinity, the atom shares correlations with the environment. Okay? So, because it's in a mixed state, right? So we start from a pure state, we go through mixed states, and this means that the information needs to be somewhere else, which is in the environment. So this means that it's sharing correlations with the environment. And which kind of correlation? So of course, we know it's entanglement because the full state of the system is pure, because initially we start in a pure state of the atom, and we start in a pure state of the environment, which is just the vacuum state. So then all together, they are in a pure state, and therefore these correlations are entanglement. However, it's actually interesting to try to understand a bit more how is the state of the full system. And it's quite surprising that for this specific open system, and almost only for this, we can actually solve analytically the problem within the approximations that we are doing. So this is what I want to do now. I want to solve analytically the problem of the atom interacting with the free electromagnetic field in free space. And we will see that we are going to learn a lot from this example. It's going to be very light. It will light up a lot of things that are still a bit unclear. And let's go to it. So, as I say, we can solve the full problem more or less analytically. So as I say, in particular, we can solve it analytically, but under the approximations that we have done. So born, not born, like you will see which ones. So the reason why we can solve this problem so easily, it's because we have a single excitation in total, right? So we start with the atom excited and the electromagnetic field in vacuum. And the only thing that can happen after some time is that the excitation, instead of in the atom, goes through the electromagnetic field. But we still have a single excitation because in the rotating wave approximation, the interaction between the light field and the atom preserves a number of excitations, as we saw with the James-Cummings model. Okay, so this means that we can use the single excitation subspace, and in particular the single excitation basis to span the states. And this means these states in here. Oh, sorry, this is A of K. Okay, so we either have the excitation in the atom and 0 photons in the field, or we have 1 photon in the field with wave vector K and the atom is in the ground state. Okay, that's all we can do. And this means that the state of the full system at any time, we can span it as some time-dependent coefficient times the times 1 basis vector, and then another time-dependent coefficient for each k, beta, times so for the other basis vectors. And just for convenience, okay, we add, like you did already in one exercise, we remove the evolution given by the free terms. And in particular, this means that we put in here this time-dependent factor, phase factor, and this time-dependent factor. So as I said, this is just for convenience, because then the equations that we find for alpha and beta are simpler. Okay? So we discount already the energies of the non-interacting terms. So this means that the Schrodinger equation, which I just remind you, we have that it's given or is generated by the Hamiltonian H light, H matter, and the interaction H light matter that I just defined before. So you can see very easily, like you already did in one exercise, but instead of for a continuum of modes, for a single mode, but it's the same kind of derivation. You can see that this Schrodinger equation leads to an evolution equation for alpha and beta that looks like this. So I don't think this is a surprise because you have already seen it a few times. Okay, and then we have beta. And then for beta, we have something similar. We have G of K. We have I CK minus epsilon T, and then alpha. Okay. Let me try to remember one thing. So how did I write the interaction? Yeah, it's fine. So you can do it for a G that is complex, and then you will get a complex conjugate in one of them, but I will just assume that G is real, okay? So then, interestingly, we can, for example, solve this equation formally. So we can just integrate this equation formally and use the initial condition of beta, which is that beta times 0 is 0, because we start from the atom in excited state. And then we end up with an equation for only for alpha that looks like this. So it's an integration of alpha. So it's a non-Markovian equation in which the time derivative of alpha depends on the history of alpha. And the history is given, so, or how far along in the history the derivative is given by this expression in here. So I think I need a bit space. Okay. And you see that everything depends on a function of tau that is this thing in here. And this function here, usually we call it, I will define it better later, so I will not say much about it now, but this is a function that we call C of tau, okay? So all the integration over K, everything that depends on K, when you integrate it out, that we call it correlation function of the environment, conjugate, you will see later why. And then you get also this phase factor. Oh, sorry, this is not T, this is the integration variable, of course, tau. Okay. So this is an integral differential equation for alpha that is exact. So we haven't done any approximation yet. All this is exact. And in particular, now if you know G, you can calculate this function in here, this correlation function. It's similar to a Fourier transform, but it's not a Fourier transform because here you have the absolute value of k, not k, okay? But in principle, you can try to evaluate this function. And then from the evaluation of this function, using Laplace transform techniques, you can, in principle, solve it analytically for any C of tau, okay? This is something that I used, for example, in one of my papers ages ago. So when I was in the PhD, I worked in models that were similar to this situation that we are studying, but with very interesting environments, not just free space, but something different. But if you are interested about it, you can always check in there, and I will be happy to discuss anything. But let's now let's now find this or solve this equation under the Markov conditions that we developed already for the master equation. And in particular, let me find this correlation function for the same level of approximation that we were doing for the master equation. So again, within the what I can call the Markov conditions. And what are the Markov conditions? Let me just specify it while I write down this correlation function. So this correlation function, first of all, I can do, well, you see that it depends only, so G depends only on the absolute value of K. The absolute value of K appears in the exponent. So this C, the kernel of the integration in K depends only on the absolute value of K. So I can do the same trick that I did before in general for any function f of k. That is that instead of the integration from minus infinity to infinity, I do it from 0 to infinity. And we get this. This is the correlation function. And now we do the Markov-like approximation, which is the following. So this is approximately equal to, first of all, we do a variable change. So we say, okay, the wave vector, we call it frequency divided by c. And second, now we do the approximations that we like. That is, first of all, the integration from 0 to infinity over frequencies. This we approximated by the integration from minus infinity to infinity. With this, assuming that the interaction is perturbative and that the modes that are not around epsilon, around the atomic transition, will not contribute. So we put artificial negative energy modes and physical artificial modes. And second, we make now the approximation that GK, it's approximately independent of K, and we can write it as gamma C divided by 2 pi, like we did for the master equation, okay? So then at this level of approximation that we used for the master equation, we get a very simple correlation function for the environment, which looks like this. Okay, and what is this? This is just 2 times gamma, the delta function of tau. Okay, so this is very similar to what we found in the when we derived the master equation for the open cavity, and so it's not a surprise that we get this kind of physics. So this automatically means that the time derivative of alpha, now, because we have here a delta function of tau, it doesn't depend on the history anymore, and it's automatically equal to minus gamma alpha. Okay, so if we come here and I tell you that C is just the delta function of tau, then you remove the integration over tau and you just get minus whatever coefficients are in C and then alpha of t. Okay, so automatically this means that alpha of t, it's equal to alpha of 0 e to the minus gamma t. And in particular, alpha of 0 is 1. So we are assuming that we start in the excited state of the atom with 0 excitations in the field. Okay? And this allows us to evaluate, and this is the important one. This is why we are doing all this, mainly. The amplitude of having a photon with wave vector k at time t. This will be equal, or approximately equal. So we just need to come here and do the integral. So now we know alpha. Alpha is just an exponential of minus gamma t. Okay. So now we have to come here and just do the integration over time. And if you do that, you get exactly this expression here. So it's just this integration of an exponential, which is very simple. You know that you get some kind of Lorentzian shape. And in particular, this Lorentzian shape will look like this. And then Lorentzian shape in the frequency, I mean. Okay. And finally, and this is the important object, the probability of having a photon emitted with momentum k is just the coefficient square. And this is equal to, so let me write it explicitly. So I get a 1 and then a number of coefficients, and that all of them will decay in time. So this is cosine of ck, so the frequency minus epsilon t. Gamma square. And frequency minus epsilon squared. Okay? So look how far we have gone. So we started asking, so what is the full state of the system? And in particular, we have been able to derive what is the probability that at time t, the atom has emitted a photon with wave vector k, okay? And it's given by this formula that now I am going to analyze and tell you a few interesting things about it, and then we are done with the lecture today. So let me point out several things. So the first one is that this probability does not depend on the propagation direction. Okay. So only on the absolute value of the wave vector, so on the frequency. So this, of course, we were expecting, but it's very nice to see it explicitly. So if you have an atom in free space, there is, so and it has a spontaneous emission, the photon can go in any direction. If you were in 3 dimensions, it could go in any direction in the 3 dimensions. If you are in this one-dimensional situation that we are describing, then this means that the photon can go with plus k or with minus k with the same probability. Okay, you have 1/2 probability that the photon goes to the right, to the left, or to the right. Okay. Now the second thing I want to mention is that if you check what happens for long times, so when the time goes to infinity, the probability of having a photon with momentum k is equal to just some prefactor and then gamma squared plus ck minus epsilon squared. What is this? This is a Lorentzian of width gamma. So, and again, this is very important because we see that the atom is not capable of emitting photons in any frequency, or at least not with the same efficiency, but it will only emit photons within a bandwidth of frequencies that are around gamma. And this justifies all the approximations that we have been discussing, that you need a resonant process, okay? You need an energy that is around the atomic frequencies. So the atom cannot emit any arbitrary photon. And actually, this is very funny because it's kind of the dual of what we saw for the cavity. If you remember, for the cavity, what we saw, so we saw the same thing, but in the opposite direction. We were trying to put light inside the cavity with a laser, right? So we took monochromatic light and we were putting it inside the cavity, and we saw that the probability or how many photons we can excite inside the cavity with a laser that is monochromatic depends on the frequency of the laser as a Lorentzian, okay? So this is kind of the dual process. It's instead of seeing how the cavity absorbs or how the atom absorbs, which we could do with a laser as well, we are seeing how the atom emits, okay? And it emits in this way. So finally, or well, not finally, but finally about this beta, it's very easy that you check on your own that what we have done is consistent, because if we integrate all the probabilities, so what is the probability that the atom is in the ground state and the field has one photon, at any time, you can check that this is actually 1 minus alpha squared. Okay, so we have conservation of the probability. These small things are important to check, okay? Because whenever you do approximations in between, maybe you lose unitarity, for example. So these things, you need to be very careful with them. So this is kind of a cross-check in the middle. And then a couple of final things about the state. First of all, the state at any time t, that is not the initial time or the final time, the infinity time, it's an entangled state. Of the atom and the field. Okay, and this you see just from the form of the state, like, because the form of the state is very clear. We have the superposition of the excitation being in the atom plus the excitation being in the field, okay? And as long as alpha and beta are not, so one of them is not 0 and the other one, as long as that doesn't happen, this will always be an entangled state. You cannot write it as a separable state of a state in the atom times a state in the field, okay? So then we have entanglement indeed between the atom and the field. And you could even evaluate what is the entanglement entropy. And the entanglement entropy will tell you that you have maximal entanglement for this time, okay? Which is the time where the master equation predicts that you have a maximal in its state in the atom, okay? And moreover, it's also very easy to check, so I let you do it, that if you do the partial trace of this state, this pure state of the full system at any time t over the degrees of freedom of the environment, what you will get is precisely this formula here, alpha t squared E projector, excited state projector, plus probability that the atom is in the ground state, times the ground state projector. Okay? What is this? This is exactly the state predicted by the master equation. So we see that when you solve the problem, the full problem, without tracing out the environment, okay, you get a pure state, which is precisely the state predicted by the master equation when you trace out the environment, okay? So we see that actually the master equation, it's very important that when we make this Born and absence of back action approximation, in which we say that the state of the system and the environment are uncorrelated and so on, we see now explicitly how that approximation that is made on the master equation itself, so on the evolution of the state of the system, of the open system, that approximation doesn't mean that the state is not correlated between the system and the environment, okay? Because we see it here explicitly that analytically we get a state that has quantum entanglement, so quantum correlations for the full system. And the master equation predicts exactly that those correlations play a big role in the evolution of the atom, okay? However, if you only have the master equation, you don't have information about the environment. So you don't know exactly how the excitations are distributed in the environment and so on, okay? That's something that we find only because we are capable of solving the problem analytically, okay? So I hope that this kind of brings you, brings light onto this open systems theory, in particular with this analytically solvable problem. So what I will start with in the next lecture is I will relax this approximation that we have made, that the coupling is independent of the frequency or the wave vector, and that we can extend the integrations to -infinity and so on, okay? And we will relax that, and we will see what happens. And we will see that this requires something that is called the Markov approximation, okay? But this we will see in the next lecture. That's the end of this long chapter. And for now, I think that is good if we just end up in here. And if you have any questions, please, now is your time. And otherwise, I will just be waiting for a while, and then you can ask me offline as usual, whenever you want. So let me stop recording.